Ding, hark, we are recording. All right, so go ahead and okay, people of the internet, I'm assuming you can all see this. The slide should say current events. Yeah, now I have to stop sharing so that I can let somebody in. Bit of a problem with the, right. And then there we go. Please type your names in the chats. All right. Okay, people in Internetville, this should say current events. And this is a bit of a review. The slide that you're seeing on the internet should say salinity. And mention that the ocean's basic composition is not thought to have changed for about the last 600 million years. That, by the way, is roughly the length of time that life has existed on Earth. Folks in the room, is that enough contrast for you to see, or should I hit the light completely? Is this adequate, or do you want it darker? Okay, thumbs up. Average ocean salinity is about 35 grams of salt, mostly sodium and chloride per liter of water. And almost all of the salt in the oceans is sodium, chlorine, sulfate, magnesium, calcium, and potassium. Okay, somebody in internet land, unmute. Are you seeing the slides changing?
Yes.
Okay, great. And as we said, salinity is not perfectly uniform in the oceans. There are areas where it is more salty and areas where it's less salty, with the light pink being least salty and the red being the most. And we talked about the reasons why this varies. So, for example, in the Mediterranean Sea, which is above the center of the map between Africa and Europe, it is salty there, saltier than average, because there's not too many rivers flowing in. I've got my mask slipped down. You've seen my nose. Ah! Right. There's not too many rivers flowing in because south of the Mediterranean is mostly desert. North of it is fairly dry as well. That's Italy and the south of France and so on. And the Mediterranean only connects with the world ocean through the Straits of Gibraltar between Spain and Morocco. Water doesn't mix very readily between the Mediterranean and the Atlantic. I guess you do have the Nile flowing in at the eastern end, but I think that's the only really big river draining into the Mediterranean. And of course, the Mediterranean being nice and warm, you have a lot of evaporation and not much fresh water coming in and not much mixing, so it tends to be salty. Even more so, this is not an example we mentioned, this is the Red Sea between Egypt and Sudan and Eritrea and Ethiopia to the left, and Saudi Arabia and Yemen to the right. This is the most saline part of the ocean that gets up to 40 parts per thousand of salt. And again, the reason's the same. There's no rivers draining into it. There might be a few, but none of them are going to be very big because this is desert country. There's not going to be a lot of fresh water coming in, probably none at most times of the year. It's warm, so evaporation happens a lot. And the only connection with the world ocean is down here at the south end, the Straits of Bab el-Mandeb, which are only about 20 miles wide. So again, this is a quasi-isolated portion of the ocean. It's not completely cut off, but still, you don't have very free exchange of water from the Red Sea to the rest of the ocean. On the flip side, there's a close-up of the Baltic. This is Germany and Poland to the south, and then this is Sweden and Finland up to the north. And the situation's the reverse. First of all, it's quite a bit cooler, so you don't have as much evaporation. It's already quite a bit rainier, and there's 250 rivers that drain into the Baltic. I don't think I could name all of them. The Nieva is up here, where you have St. Petersburg. Up here, you've got the Gotha Elv. You've got a bunch of little fiddly ones down here whose names I feel like I should remember, and I can't. But anyway, there's a lot of drainage coming in, especially in spring. This is not something that we see a lot of in Arkansas, but in places where they actually have a winter that lasts for more than 3 days, you have a snow, of course, building up during the winter, because that happens up there. And then when it melts, you've got a big pulse of fresh water coming down the streams, which can swell quite a bit with all that meltwater, and all flood right into ultimately into the Baltic. That flood of spring meltwater is called a freshet, by the way, like the word fresh plus et. That's the freshet. Nice little literary word right there. And also the Baltic is, again, not fully, well, I don't want to say not fully connected, but there's only a narrow connection between the Baltic Sea and the North Atlantic. Right up here, this little strait between Denmark and Sweden called the Kattegat. And if memory serves, it's also kind of shallow right there, and it's rather tricky for navigators because you have shifting sandbanks and things like that. So the Baltic is kind of semi-isolated. Most of it's actually said to be what we call brackish water, which is salinity anywhere from 30 parts per thousand to 0.5. And you can see you've got a great gradient between the more saline water up here at the Kattegat, and then when you're back here at a place like St. Petersburg, Russia, where you've got 2 parts per thousand or maybe a bit less, that's getting very close to being fresh water right there. Okay, right. As we mentioned, you can have rivers that will send fresh water into the ocean. And one thing that you can remember is that salt water tends to be more dense than fresh water. So that when a river sends fresh water out into the ocean, they eventually mingle. But possibly for hundreds of miles, you'll get a plume of fresh water kind of floating on top of the salt water and affecting conditions in the ocean, maybe hundreds of miles out to sea. Eventually everything gets mixed, but it does take a while. So right here, this is the coast of South America. Right there is the mouth of the Amazon River, the largest river in terms of sheer volume of water that gets pumped in, that gets pumped into the ocean at the mouth. And right there, that blue area, that's that plume of salt water coming out of the Amazon. and you can trace it, that yellow zone, you can trace that all the way to the right-hand edge of the map. That's the kind of effect that rivers can have on localized parts of the ocean. Okay, now that we've covered salinity, I want to talk about currents. And there's a connection between them. If you look at the density of seawater, it's also not equal everywhere. Because first of all, salt water is denser than fresh water. That's why you get those plumes. The fresh water will kind of rise and salt water will tend to sink. And it's also correlated with temperature. Fresh water reaches its maximum density at 4 degrees Celsius. You might remember that water, never mind. Fresh water hits maximum density at 4 Celsius, but salt water just gets denser and denser all the way down to the freezing point. So you can have salt water down below 4 Celsius, and it will just keep getting denser and denser until you get to the point that ice crystals begin to form. So you might notice that seawater freezes at a lower temperature. This is why you spread rock salt on icy roads. The presence of that salt lowers the melting point, lowers the freezing point. Same thing. This sets up a global pattern. The densest water is what you find in the Arctic and the Antarctic. First of all, because it's the coldest. And second of all, here you've got some sea ice in the process of forming. And when you take a water solution of something and you freeze it, the water goes into the ice form, and whatever was dissolved in the water tends to stay behind. Now, one thing you should never do, because this is illegal and you could get in trouble, under federal law, you're not allowed, you can ferment your own alcoholic beverages if, of course, you're over 21. I know you would never violate that law. But you're not allowed to increase the content of the alcohol more than what fermentation can do. So you are strictly not allowed to distill. And another thing that you're not allowed to do is take an alcoholic beverage like beer or wine and freeze it. Because if you did that, what you would get would be a mass of ice crystals. And the ice would be mostly fresh water. And the ice crystals would be floating in a liquid. So you get kind of a slush. And the liquid part of the slush would contain most of the alcohol. So if you were to freeze some beer until it turned into slush, and then strain out the ice would contain the fresh water, and the alcohol would go into the liquid that was left behind. And you would have a fortified alcoholic beverage, which of course is illegal, so you're not ever going to do that. Right? Right. Good. Yes, we are law-abiding citizens here at UCA. Incidentally, people used to do this up in the northern U.S. with cider. You know, you take apples and you squish them and you make cider. They let the cider ferment and then let it freeze over the winter and then strain it out in the spring, and you've got a drink known as Applejack. Yeah, that's what it meant before it meant an exceptionally sugary breakfast cereal. Applejack was fortified cider made by freezing it and straining out the water. Okay, now that I've told you how you are not going to violate the law, the same thing happens in the Arctic and Antarctic when it gets cold enough for seawater to freeze. It's the H2O itself that ends up making up most of this ice. And just as alcohol is left out of the ice and stays in the liquid phase, the same thing happens for the salt. So the water that's left behind as sea ice forms is not only extremely cold, it's also extremely saline, and those two factors together make it very dense. So guess what happens to dense things? Yeah, they sink. And this sets up a global circulation pattern called thermohaline circulation. Thermo, of course, means temperature. Halos is ancient Greek for salt. For the record, I'm never going to ask you what is the meaning of such and such a word in Greek or Latin. Not that I'm not tempted to at times, but this is not that kind of a course. But I will often explain words in terms of their roots. Sometimes that helps people remember vocabulary. Sometimes these roots turn out to be useful in other classes, or possibly even professionally. If you study microbiology, you might encounter halophilic bacteria. If you know that halo means salty, you know that halophiles are bacteria that grow under salty conditions. For that matter, there are plants that grow under salty conditions. They're called halophytes. Now you know why. Right, so the thermohaline circulation starts up here at the poles, where you have warm water that cools off and freezes, and what's left behind from the sea ice is very cold and very dense saline water that very slowly sinks down and flows in this circuit that you're seeing that might take a given molecule maybe 1,000 years to complete. This is very slow, long-term circulation. But this cold, salty water will sink until it reaches the bottom and then kind of spread out over the bottom of the ocean and set up this giant conveyor belt that might end up only emerging back up here in the North Pacific and then returning by surface flow back to where it came. So again, this is extremely slow flow, but it's critical for life in the deep ocean. There have been times when that hasn't worked. Typically times in Earth history where temperatures were warmer and we didn't have sea ice forming. And when that has happened, one of the effects has been that thermohaline circulation stops. That slow conveyor belt driven by changes in salinity and density doesn't operate anymore. And one of the things that we see when we look at the fossil record of times like that is large areas of the ocean floor becoming anoxic. There's not humongous amounts of oxygen down there at the best of times, but thermohaline circulation transports enough oxygen down to the bottom of the ocean floor that critters like Anoplagaster, I can't remember what they called it, like a fang tooth or something like that. This deep sea fish can get enough oxygen to survive. And at times when we haven't had this vertical mixing of ocean water driven by density differences, the bottom of the ocean becomes anoxic, and we don't see critters like this that can't live under such conditions. Okay, are we happy there? One thing that I didn't point out is that salinity is lowest at the equator. I'm not going to go back through all of the slides, but if you go back and look once I get these posted, you'll see that there is a stripe of less saline water right along the equator. It's a little bit less salty there than it is in the mid-latitudes. And the reason is that there is a zone of very heavy rainfall along the equator. And you can see it in the satellite picture. You're looking at southern Mexico, Guatemala, Central America. Here's Panama. There's Cuba, by the way. And then this big continent is South America. And running, there's the Galapagos. And running very close to the equator, it's just a little north of it at this time of year, you can see a big band of clouds. That band of clouds is called the Intertropical Convergence Zone, the ITCZ. Because of the tilt of the Earth, the ITCZ actually moves north and south, which means that if you live, let's say, here, there are times when it's right overhead and times when it's well to the south of you, which sets up the primary seasonal pattern in the tropics. Not summer versus winter, because it's pretty warm all the time, but wet versus dry. A lot of tropical locations, the difference is not between a warm season and a cold season, but a rainy season and a dry season. And some of that is due to the fact that the convergence zone can migrate. Okay, whoa, with me. Why is this happening? Why do we have that convergence zone? You can go watch some water boiling in a pot and start getting an answer. There are three major ways that heat can travel. One is through radiation, basically in the form of electromagnetic radiation, light, or ultraviolet or infrared or something like that, traveling through space. That's how the sun makes the Earth warm. Right? That's how energy gets from the sun to the Earth, even though that's about 93 million miles of hard vacuum that it has to travel. The second way is conduction. If I was to take this piece of metal and stick one end in a fire and just hold it right there, heat would essentially flow up this piece of metal and burn my fingers if I gave it enough time, right? Okay. The third way that heat gets transferred is convection, which is heat transferred by the flow of a fluid. So if we've got a pot of water on a stove, you have your heat source at the bottom. That heat source warms the metal of the pot by conduction, and that warms the water at the bottom of the pot, and then the warm water at the bottom of the pot begins to rise. As it rises, it cools a bit. It loses heat up here at the top, so it cools down, and as it cools down, it sinks. And you get this pattern of circulation. In a pot that's just about to boil, you can even see fairly stable convection cells. Just like there's columns where water is rising and sinking. You're not quite at a full rolling boil where that happens. Yeah, go home, take some water and heat it up in a pot and like really look at it, man. You ever really looked at your hands? Dude, okay, sorry. Momentary flashback. Right. So this is a case of convection. Heat is getting transferred from the burner through the water, and then as you'll feel if you put your hand over it, some of that heat is getting transferred to the air above it, and the transfer is being done by the fact that fluid is flowing, carrying the heat with it, you might say. Okay, the same thing happens in the oceans, and the same thing happens in the atmosphere. Because when solar radiation passes through space, most of it passes through the atmosphere, except for the ultraviolet energy that's absorbed by the ozone layer. But most of the energy that the sun puts out reaches the surface of the Earth. You can tell by the fact that, like, the sun is bright. right? If our atmosphere blocked solar energy, then it would be completely dark outside. But yeah, much of that energy reaches the surface of the Earth. It heats up the land. As you can tell if you have ever walked barefoot across an asphalt parking lot. Anybody ever do that as a kid? You're real eager to get to the swimming pool and you don't bother with putting on your sandals, and you end up doing this crazy dance, boing, 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 until you can either get to the pool or give up and put your sandals on like Mama told you to. Yeah, been there, done that. So as you can tell, solar energy falling on the land makes it hot. How hot depends on what type of land it is, of course. Asphalt tends to heat up very fast, grass not nearly as rapidly. But the heating of the land, in turn, heats up the atmosphere. And right about where the equator is where the sun's rays are hitting the most directly. And they heat the land the most, and the land heats the air, and the air begins to rise. So close to the equator, you have this band of hot air that's constantly rising. With me there? As that air rises, it cools off because it's under less pressure. You might remember your gas laws. Anybody remember PERV-NERT? Sorry, pressure times volume is N, number of moles times R, the gas constant times temperature, PV equals nRT. Sorry, I always remembered it as PERV-NERT. Maybe some of you did too. Right. So if you decrease the pressure of a volume of gas, you decrease its temperature as well. You may have noticed this if you've ever held an aerosol can while you were spraying, right? The pressure in the can decreases, the temperature does too. As you spray, the can feels cool. On the flip side, of course, if you've ever pressurized gas, like pumping air into a bike tire, as the pressure increases, so does the temperature, and bike tires can get pretty hot if you're pumping them up. Right? You have heard all this, probably heard it back in Physics 1. Yeah, okay. All right, same thing happens here. As that air rises, it cools. Here's the thing about air. Hot air can hold more moisture than cold air can. I know this because it's been really hot here for a while. And on days when it gets really hot, my air conditioner, my window unit, starts leaking. Typically right on my pillow, damn it. And the reason is that air conditioner is cooling off a lot of water, or cooling off a lot of air, and the air is very hot, which means that the air holds a lot of water in it. Right? Hot air has a very high capacity for water vapor. Cold air, not so much. This is why, yeah, when I take that hot air from the outside and cool it, the cold air that the air conditioner is making can't hold as much water vapor. So a lot of that water vapor falls out and turns to dripping on my damn pillow. Right? Maybe you have had window units that did something similar. For that matter, if you're sitting outside and you get a nice cold drink, right, the cold air right next to your drink loses the ability to hold water vapor, and you get beads of water forming on the outside of your cup. Right? Everybody's had, a cup appear to sweat. It's not really sweating. What it's doing is condensing water that was water vapor in the atmosphere. Okay, where am I going with this? As that air rises at the intertropical convergence zone, it cools off. As it cools off, it drops its moisture in the form of rain, and that's why you have a band of very rainy weather around the equator. That's why you have the intertropical convergence zone. You with me there? Okay, now the water rises, the air, rises. It drops its moisture, and it circles around to the north and also to the south, and it comes down at about 30 degrees north and south. Notice that when it's, first of all, as it comes down, it warms up, because as it comes down, its pressure increases. So you have warm air coming down at 30 north and 30 south. Notice that it's also dry air, right? Because it's already dropped all of its water back here at the equator. So what you have is a circulation pattern called a Hadley cell, where air rises at the equator, circles around, and comes back down to the surface at about 30 north and 30 south, right? And so the rising air at the equator dumps a whole bunch of water. This is by and large the rainiest part of the Earth is close to the equator, right? This is where you get, the tropical rainforests of Africa and South America, for example. And then where you have dry air coming down to the surface at 30 north and 30 south, this happens to be where the world's deserts are located. So here's that slide I just went through actually restates what I was talking about. But in the interest of time, I'm going to move on. Here's a global map of average yearly rainfall. There is a great big stripe of very, very rainy weather cutting right across the Pacific. Right? See that big purple band? For reasons we'll get to in a minute, having continents in the way tends to mess up this pattern, but you can still see a lot of rain in tropical South America. That's the Amazon rainforest. You can still see heavy rain in tropical Africa, and then over here in tropical Southeast Asia, in Malaysia, Indonesia, New Guinea, all of this. Now this rain belt actually hooks north and south, and I'll talk about that in just a minute. I'll get to it. But then if you look at 30 degrees north and 30 south, well, in Africa, 30 north is right in the middle of the Sahara Desert. 30 south, right here, you have the Kalahari Desert. If we look over here, 30 north is about where Saudi Arabia is, and that is mostly desert, the Rub al Khali Desert. Some mountains mess up the pattern a little bit, but we have this desert belt up north of India, the Taklamakan Desert, which I'm told is, in the local language, means enter once, never leave. Yeah, don't want to get lost in the Taklamakan. South, you have Australia, which is mostly desert, except there's some tropical rainy areas up here in the north, and some pretty tolerable areas along the coast, but the interior of Australia is almost all desert. And then in North and South America, up here we have the Mojave Desert and the Chihuahua and Sonora deserts up here. And in South America, at about 30 south, you have the Atacama Desert, which includes a town that has had no rainfall recorded in 400 years. Yeah, that's actually part of the reason why astronomers like building very expensive telescopes in the Andes Mountains up here. Very clear air and very, very unlikely to get rained out. Okay, so that's why we have deserts concentrated at 30 north and south. And at the equator, you can see that intertropical convergence zone. Now, what about these hooks right up here? Why does this rain belt go across the Pacific and hook to the north and to the south? And then why do we have this rain band up here? Well, to understand why, we have to use the force. Specifically, the force that was discovered by the great Jedi Master Gaspar Gustave de Coriolis, who used the Coriolis force. All right, there he is using Coriolis force. You know how you can tell that Star Wars did not take place in Arkansas? Darth Vader would have said, "No, Luke, I am your father, and your uncle, and your cousin, and your nephew." Okay, sorry about that. Right. Okay. The Coriolis force does not involve picking up rocks with your mind and chopping at your dad with a lightsaber. It involves the fact that the Earth is turning, and the spin of the Earth means that anything that is moving above the surface of the Earth tends to veer. So anything that's moving over the surface of the Earth gets deflected to its own left or to its own right. There's a classic Calvin and Hobbes that explains how this works in 2 dimensions, where Calvin's dad, okay, he's playing a record, and you kids probably have no idea what those are, right? Little black things that go around and around and around. And then sometimes people stop them from going around and around, and they go. Okay, anyway. All right, so here's Calvin playing with his ancient artifacts. And there's a record going around. Calvin's dad points out that a point near the center and a point at the edge both make circles in the same amount of time. Right? If this is a 33 RPM record, it will take roughly 2 seconds for a point at the center or a point at the edge to go around once. Right? Yes? But the point on the record's edge has to make a bigger circle, so you have 2 points that are moving at different speeds but making the same number of revolutions per minute. You probably don't find this as especially fascinating, but evidently Calvin is completely freaked out by this knowledge. It works on a spinning globe as well. Let's say we have a crazy dictator who decides that he wants to kill Santa. So he buys a great big cannon, and he puts it here on the equator, and he fires an extremely powerful cannon shot right at the North Pole. What happens? Well, if you're at the equator, then you and everything is moving roughly 1,000 miles an hour, or about 1,660 kilometers an hour, because the Earth is rotating. You know, it takes, I feel like this is an act of political courage to say this, but the Earth is goddamn round and it's spinning, okay? All right? I don't care what the little people in the Google who are talking about Q are telling you. The Earth is actually round and it goes spin, spin, spin. Sorry, not trying to get political here, but I speak the truth. And this is part of the way that we know. So when the cannon is right here, the cannon and the cannoneer and the land that they're sitting on and everything is getting dragged around from right to left, from west to east, getting dragged around at roughly 1,000 miles an hour. When the cannon fires, the cannonball moves north, but the cannonball is also getting dragged west to east at 1,000 miles an hour. With me there? The problem is the cannonball starts veering farther north. The cannonball is still going at about 1,000 miles an hour west to east, but the land that it is passing over is not going that fast. So what that means is that seen from the ground, the cannonball veers to the right. And in fact, everything in the northern hemisphere will veer to its own right. It's not the sort of thing that you would easily observe on a human scale. People started, Coriolis described this back in 1800 and don't care, but it started getting noticeable in World War I when armies started building cannons that could shoot targets that the gunners couldn't see. Back in Civil War time, usually you fired at things that you could actually see. Partly because there was no way, back in those days, usually no way that you could check your accuracy, right? You could you could fire a cannonball 5 miles, but you'd have no way of knowing whether you were on target or not. But by World War I, you have more powerful guns, and you have spotters that can tell you whether you're on target or not. People in airplanes and balloons. They didn't really have that in the Civil War. They did experiment with balloons a bit. But this means that it's now feasible to fire shells at targets that are over the horizon. Right? You can put a bunch of guns on a battleship and blast the heck out of forts on a coast without ever getting close to forts. Right? You can do the same thing on land. You can shell targets that are not line of sight. And when that was made possible, it turned out that gunners had to learn to correct for the Coriolis effect, because their shots in the northern hemisphere would always end up veering to the right of where they thought they were aiming. Somebody worked out that the effect of the Coriolis force on a typical baseball hit works out to be something like 1 inch in 400 feet. In other words, it's just possible that it could make the difference between a screaming line drive down the left field line and a foul. I mean, it would be really, really close, and probably you'd have a lot of other things to take into account, like wind and stuff like that. But it's just possible it could make the difference between a home run and a foul. Okay, and then of course, if you're shooting artillery shells at a target 15 miles away, you definitely have to correct for it. So how does it, yes ma'am?
Is deflection higher to approach the equator or the pole?
The what, air pressure?
Like, how much an object is?
Oh, how much the deflection is? I don't think there's any change in the deflection. There's just more deflection the farther you go. But I don't believe that because the Earth is close enough to a sphere that it makes not much difference. It might be different if the Earth was shaped differently. But since the Earth is very close to being a sphere, I don't think the force changes as you go from south to north. I could be wrong about that. It's never happened, but there is always a first time. That was a joke. Right. How am I doing on time? I can't see. All right, 9:47. Okay. Last thing that'll give you some perspective on current events in the Gulf of Mexico. Where you have lots of air rising, air pressure is low because the air is not pushing down, it's being pushed upwards. And we recognize areas of low pressure on a weather map with a big capital L. You've probably seen that if you've looked at weather maps before in the newspaper or AccuWeather or what have you. And the thing about the atmosphere is you can't dig a hole in it. If you make air move somewhere, more air comes in and fills it. You cannot rip a hole in the air. Well, okay, maybe you kind of could if you're like traveling at several times the speed of sound or something like that. But under ordinary weather conditions, you can't tear a hole in the air. So if air is rising, then more air has to come in from the sides and fill the gap. Right? Yes? Water is the same. You can't tear a hole in water, at least not by ordinary processes of flow. Like you can if you have a super fast ship propeller or something like that, but under the kinds of conditions that living things encounter, you can't rip a hole in the water. So that means that if you have an area of low pressure, air flows towards it. Right? If I take air and I push it up, then air comes in from the sides and fills in the space. The problem is that the Coriolis force, if you're in the northern hemisphere, deflects that air to the right. Everything goes to the right in the northern hemisphere. And that sets up a net counterclockwise circulation going around that zone of low pressure. And we call this cyclonic flow. To a weather person, a cyclone just means an area of low pressure that has rotating air going around it counterclockwise. In common speech, cyclone is often used as a synonym for tornado. I guess a tornado would be, what is it? The Iowa State mascot is the Cyclones, and I think they mean tornadoes. But a tornado would be a cyclone, but not every cyclone is a tornado. Cyclone is just this counterclockwise flow around a zone of low pressure. So a couple of years ago, we had Hurricane Irma in the northern hemisphere, and if you trace the direction of those rain bands, they're spiraling in towards the center counterclockwise. That's what a northern hemisphere hurricane looks like. They have them in the southern hemisphere, although they usually call them typhoons, but it's the same basic pattern. So if you knew nothing else, you could tell this picture was taken in the northern hemisphere, and Cyclone Fontala a few years ago off the coast of Madagascar in the southern hemisphere is spiraling in the opposite direction. It is spiraling clockwise. This is why you hear the story that water flows down a bathtub drain counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The actual truth is that you would need a perfectly shaped bathtub to be able to observe this, because on something as small as a typical bathtub, the main thing that determines what direction the water spins as it goes down is basically irregularities in the shape of the tub and like any splashing that you might have done in the tub and things like that. So you really have to observe it with an extremely precision-shaped bathtub to be able to see this. But even if you can't see it in a bathtub, you can see it over larger scales of space, like hurricanes and cyclones. Okay, I have not yet gotten to why you have those rain bands in the temperate latitudes, but when we return on Wednesday, I'll have more to say about how the Coriolis effect affects global weather patterns, and I promise I'll get back to the oceans, and we can talk about how this affects global current patterns. So we'll talk about current events when we come back on Wednesday. Yes, those of you that are here, go ahead and email me something to the effect of, "Hi, I was here." All right, people in internet land, I'm going to go ahead and shut this off, and then we can cuss. Okay, everybody was here. Were you guys were able to see all of those slides? Okay, here, I'll stop recording just a sec, and recording stops now.